So somebody has posted saying that the Moodle wasn't loading for people, so they have shared a link. So I think people will be joining in now. So can we wait for 1 more minute? I think is that okay with you?
Yeah, I'm okay. But why would they? They also must have got by email, huh? The link.
Yeah. So that is also fair. Yeah, Moodle wasn't loading for people, so they have.
Oh, you mean the Zoom was not loading?
Is that okay with you?
Yeah, I'm okay. But why would they? They also must have got by email, huh? The link. Yeah, that's what I was saying.
That is also fair. Yeah, Moodle wasn't loading for people, so they have.
Oh, you mean the Zoom was not loading? Yeah, I'm okay. But why would they also must have got by email? Huh? Yeah, that's what I was saying.
That is also fair. Yeah, Moodle wasn't loading. So I think there's some echo on your end.
Oh, you mean the Zoom was not loading? Yeah, I'm okay. But why would they also must have got by email? Yeah. Hello, can you hear me?
Yeah.
Okay. I think that echo was because, no, I mean, I had turned on this collab. So let me, yeah, we can wait for a couple more minutes because we're still getting adjusted to a lot of changes now. I don't know, was everyone fine with this 5 p.m. thing? You know, so, or is there some people who expressed,
See, I think people, someone did say that like it was bad that like the evening canteen times were being encroached upon. But I mean, I think this is the sort of the only slot that we have in the like post lunch session, at least according to the spreadsheet. So,
but no one expressed they were dropping because of the lateness, did they?
I hope not. No one did express that, but I hope not that like, that is the reason that people are dropping.
Okay, so what I want to do is, since at least it's my first class, let's say, may I request you to turn on your videos so we can see faces. If you don't mind. Hi, so I'm Srivas. I've been with CMI for what seems like forever. So it's from 2011, I think, 2012, more than 10 years. I used to work for lots of companies, startups, and some multinational companies. My area of interest is in applying formal verification synthesis. So it's an area of using applied logic for various analysis of computer systems and artifacts. And my recent interest has been to look at machine learning, both from the point of view of further this scale, to further the scalability aspect of using logic for various analysis purposes. Okay, and this is one of several courses. Most of my courses have been in this area. In the thing for yeah, so generally in this area of applying applied logic is what I would call, and also design of things. And I'm also applied for hardware systems. I'm interested in digital systems, synthesis, software, and things like that. And it's currently machine learning. Okay, so Diganta, and then we'll go in order of how the pictures appear. Now called for people.
Right. So
go ahead, Diganta.
Yes, hi, I'm Diganta. So I was there at CMI for BSc and MSc. After that, now I've joined TCS research. So I'm also really interested in formal verification and sort of applied logic. And also more than that, I'm really interested in applying formal verification to machine learning and systems, in the sense that, looking at a DNN or some other machine learning system and trying to figure out if we can prove some safety properties of this system in that. So, and in general, the intersection of machine learning and formal verification really interests me. So that is my interest in some sense. And yeah, I guess that does for an introduction to the field.
Okay, next is yeah, just say something. I mean, if you certainly I want to hear what year, okay, BS, MS, and your branch.
Sir, I think your voice cut off when you said the name of the person.
Rohan
Yeah.
Dharmadhikari.
Yeah. So I'm Rohan Dharmadhikari. I'm an MSc Data Science second year student here.
Okay.
And I have a background in civil engineering before this. And like I've been coding before I've joined this course. So I'm familiar with Python quite a lot. And when we were studying machine learning last year, neural networks caught my eye, and I worked on convolutional neural networks for my internship as well in the summer. So this is why this topic was a little bit different for me. And after the first class also, the interest peaked for me. That's why I'm here, and
Okay.
I want to learn this.
Okay, good. Shauriyam Kauri.
I'm a yes audio. Maths and CS. I'm audible.
So you're kind of breaking up. Can you repeat? Shauriyam.
Yes, I'm audible.
I think if your voice is breaking up, you might maybe even turn off the video for a while because it takes up some bandwidth.
Yeah,
Okay, then maybe we can do this since we're all seeing face. Yeah, I mean they could do that. Yeah, does it help? Shauriyam, you said second year MSc or third year BS.
Third year BS. Yeah.
BS. Okay. In CS and math?
Sir.
In CS and math? Is that what I understand?
Yeah, I think it'll.
Yes, sir.
Yeah, his thing is break up. Okay. So let's move on. Soham.
Yeah, hi. So I'm a MSc Data Science second year student. So my interest is something like, I mean, in the summer I was working on explainability, interpretability aspects. So I studied some of causal inference and some part of it. So this is one of like this course seemed interesting and like this logic, and I mean it was kind of a similar flavor to that. But yeah, so that is why I took that.
Okay, so maybe then have you looked at explainability, interpretability, what it means in the context of DNN and so on as part of your machine learning course?
Not yet, no.
Not yet. Okay.
But we'll be having some part of it.
Yeah, maybe as on some as part of advanced, we'll be looking at certain properties, mostly robustness and safety and these consistency properties, but interpretability and explainability are very interesting. And maybe, towards the end of the course, we can look at that. And then maybe if we have time, study some works, okay, that have been done, okay? And, whether we'll get to using logic for that or not, we'll see if we can cover that aspect of the course. Okay. Nabin Sahu.
Yeah. So I'm MSc first year, CS.
MSc Computer Science?
First year, CS, Computer Science.
Oh, okay, good. Yeah.
Yeah, I did my BSc from CMI, and
okay.
yeah, I am interested in logic and machine learning as well. So like I did an internship last year on machine learning, and I did an internship on logic this year. So like this course seemed like a nice combination of both. So yeah.
Okay, so welcome to the course, and I hope we'll find it interesting and productive. Okay. Next is we went Ashutosh. No. Shauriyam we've already gone through. Yeah, Ashutosh Maurya.
Yeah, hi. I am Ashutosh, and I'm in the MSc Data Science program and in second year. And like Soham, I have been working on the responsible AI in my internship period, and I was mainly looking in the bias and fairness aspect of machine learning models and neural networks. So basically, my motivation was that also to this formal verification really interested me. So
Okay.
that's why I took the course.
So, I mean, I missed the part. I mean, you are MS or BS?
No, MSc Data Science, second year.
Oh, okay. Yeah, Dribijyoti wants to type his comments. Okay, so I'll read out. So why don't you
Sorry, did you say something?
no, Dribijyoti. I'm moving on to Dribijyoti. Dribijyoti. So BSc third year, good. So you've had logic. Have you have been exposed to machine learning or logic, either of them, Dribijyoti? You are taking simultaneously with this logic. Okay, good. Yeah, I mean, it's a mix. I mean, I see more data sciences here. And so which means that I guess, I mean, the people, at least half the people have been exposed to machine learning. So of logic, and you will see that the logic here, you have to feel so there are formal logic courses. There are people who have taken it would have seen that those logic courses are go deeper into the formal aspects of logic, and they start proving theorems and so on. Yeah, I mean, I know Dribijyoti said that he has no experience in ML. That should be okay if you could do the first few exercises. See, the first couple of assignments, as I described in the course summary, the first one will be on machine learning, using TensorFlow, and the second one will be on using this constraint solver called Z3 on a few examples. Now, if you are, as I was saying, even if you have not had exposure to a logic course, but if I think you should have had exposure to some discrete math course. If you're able to, we'll be looking at logic more from a user's perspective, how you could use logic to model and, do certain interesting things, solve certain interesting problems, in this case, particularly for DNN. Therefore, if you're able to comfortably do those two exercises, one on machine learning using TensorFlow, and the other one, some logic examples using this Z3, which I hope you'll be able to do before, at least you'll be able to go through the lectures before August 19th. You should be able to deal with the course. Okay, so today I'll give some introduction to logic, and if you're comfortable with that and it's not too complicated, you'll be fine with the course. And if you have the next two lectures, you are able to manage, understand the thing, and then along the way I'll be giving you some home exercises, class exercises, and then if you take the initiative to do it using Z3, then and feel comfortable enough, then I think you should be okay with this, with the course. Okay. So since I've already spent, I should be recording. No, I've already started live stream. Therefore, that should be okay.
So do you think that this few slides from last time, I can talk about them, or should we do it later?
No, I think you should. You should. Okay. So what we'll do is, there are some loose ends that Diganta wants to tie up from last class, and then I will start. So that's okay. So we can take it. Go ahead. So
sure, sir. I'll start.
But let me also start recording. Okay. This is
So, sir, can you also make me
Yes,
co-host?
I will do.
Thanks. Yeah, so hopefully you can see my screen. Right. So
Yes.
basically, I just want to quickly, like, I think I got cut off last time because of some technical issues. So I just want to quickly just finish up what I was saying. That's all. So basically here I was just comparing like DNN verification with program verification, and the main, I won't really take too much time. So I'll just say what the main point that I was trying to make was. But the main point is that, like, with programs, there is a lot of structure that you can leverage. They're usually modular. And also there's, since they're designed by humans, they usually have some simple underlying logic, right? So because of this, we have some sort of way in which we can understand programs, and we can leverage that when we're trying to verify programs. And in general, program verification is much older than something like DNN verification. So all of these things have been done and people are still continuing to do it. So it's a fairly mature field in that way. Comparatively, DNN verification is new, and DNNs are, best treated as black boxes when constructing them, right? So in the training process, we don't really think about what each neuron is doing, for example, right? So in that sense, it has got little structure and almost no design or modularity. So all of the tools that we have on the program verification side, it's very hard for them to sort of translate to DNN verification. And we don't really have, compared to program verification, we don't have that long of a sort of length of research for DNN verification is not that much. So in that sense, it's challenging. But also, let's look at DNN verification from more like why they're challenging from a more theoretical aspect, right? So one of the things that one always looks at whenever we're trying to model or verify some system is how expressive it is. In the sense that if you look at it as a function, then what kind of functions can this system emulate or be, essentially, right? So DNNs are, function approximators, right? So the main theorem, there's this couple of theorems which are called universal approximation theorems. So what they say is that DNNs can actually approximate any function if you allow them to be sufficiently complicated, right? So there is some formal set of constraints in the statement of the theorem, but the basic idea is that if you have any continuous function and any sort of epsilon, then you can have a DNN that like approximates this function up to epsilon with just one layer, but that layer should be arbitrarily large, right? Similarly, you can have another DNN that does the same thing. This time the layers are bounded, but then you'll have to allow arbitrarily many layers. So in this sense, like if you let your DNNs be as complicated as you want, it can sort of approximate any continuous function you throw at it up to any degree of accuracy that you like want, right? And if you look at the sort of class of functions that continuous functions can be on a compact space, mind you, but like if you look at the class of functions that continuous functions can be, then it's a very huge class, right? So if you had sort of a very good push button way of proving some properties for DNNs, you could imagine that you might be able to translate some of that for arbitrary functions from R to R, which sounds too good to be true, right? So this is another sort of aspect of it in some sense, why this thing is hard or should be hard in some sense, right? So if you have any questions, just please stop me. I will not pause separately because there's not too much time. I've got some statements here, and these are uploaded already, so you can look at them, the formal statements of these theorems. But there is another sort of a third way of looking at why these things are complicated, and this is, or why DNN verification is hard. And this is basically showing that DNNs are complicated in the same way that, say, a logical formula can be very complicated to analyze, right? So you see, expressibility in this way that I have talked about in the last theorems, that's not something that is unique to DNNs. Even polynomials have that, right? Like you can definitely get a complicated enough polynomial that will approximate any function up to whatever degree that you want. That is, I think, called the Stone-Weierstrass theorem. Hopefully, I'm not getting this spelling wrong, but like, yeah. So that is that is there. So in that sense, that is not very, unique to DNNs. But as a function approximated, DNNs are somewhat compact in the sense that if we add one neuron to a DNN, that will allow us to capture exponentially more detail, right? So let's consider the special case of ReLU DNNs to understand what I mean by this. So these are piecewise linear functions, right? Now let's say that we add one neuron. So what can happen in the worst case, and you can't really show that this won't happen, but what can happen in the worst case is, say, if you have some pieces like this, and your DNN behaves linearly in all of these pieces, what might happen is the addition of this single neuron might cause all of your pieces to split. So you might end up getting a split here, a split something like this maybe, and maybe a split here and maybe a split here, right? So now whereas previously you had got 4 linear pieces, now you've got 8 linear pieces, right? So in this sense, adding a single neuron can lead to exponentially more nonlinear complexity. And while I stated this for ReLU DNNs, you can actually sort of imagine a similar situation will happen with other DNNs as well. Whereas there, things are not piecewise linear to begin with. But like I said last time, there is still some notion of almost linearity that we can think of in regions of almost linearity. And those regions will again can multiply exponentially, right? So this fact is basically crucial in proving, this really important fact that DNN verification is actually NP hard, right? Or this fact lies the heart of that. So I just very quickly give you how you can prove this. I'll not go into too much detail, but the fact is, or the core of this is that you can, encode and such things as DNN. So you can have a DNN that actually behaves like an AND function in the sense that if you pass it 0, 0, it should give you 0. If you pass it 0, 1, it'll have 2 inputs and 1 output. It'll give you 0. If you pass it 1, 1, it'll give you 1 and so on, right? Of course, it's a continuous function, but I'm saying that on these discrete values, it should behave exactly as AND should, right? And you can construct this. You can think about it a little bit. It's not very hard. So then if you can do that, then of course you can construct any Boolean function. You can convert any Boolean function as a neural network. You can encode this very easily. Right? And notice that this encoding has linear size, right? Because whatever DNN you have for AND, this will be some constant size DNN. So if you have a function that has got, say, k many ANDs, you'd have k times whatever the size of this AND DNN is that you come up with. It doesn't matter, right? Whatever the size is, you'll always have a constant or a linear size encoding. So then, if you have any arbitrary SAT query, so sir will get into exactly what a SAT query is, but basically there is this question where given a formula, can you find some assignment for variables where the formula is true? So that can again be encoded here, right? So the precondition will just be for your DNN verification queries that inputs are between 0 and 1, and the post condition is output is 1, right? So if we can actually verify this, then that means that or say that the post condition is output 0 actually for SAT. But essentially, if we can verify this means that the formula will be SAT. And then what we have achieved is a reduction, right? So essentially, if you're given this question of given a formula, is there any assignment that will give me 1 as a result? You have reduced that to actually given a DNN, can we check certain properties for this DNN, right? Now, it is actually, conjectured and widely understood to be or expected to be true that this question of, this SAT query, it's widely considered to be that, it's not possible to solve it any faster than exponential time, right? There's a class of problems that are of this particular nature, and there's some formal definition of it, but it belongs to this class called NP-hard problems. And since we have shown that if you can solve DNN verification, you can also solve this problem. This means that DNN verification itself is also NP-hard, which means that we will actually expect any algorithm that is guaranteed to produce an answer. We have to expect it to be worst case exponential, because if you have found an algorithm that is not worst case exponential, that is profoundly too good to be true in some sense, right? So so these are basically some of the, these are all the slides that I had. So if I have any questions, otherwise I think that's all I have.
Yeah, we will. I mean, yeah, in my lecture, you will hear more about SAT, and I think. Okay, any questions about DNN? I mean, I think there'll be as I said, an assignment will go out very soon after a review, probably as early as next Monday, in which you will be asked to design a neural network for a particular task of character recognition, which you will train and train using TensorFlow. So, and there'll be a tutorial that we're asking Hirsch to do. So those things will be there. The general, so you can use. Any questions about but more about this NP hardness of SAT query, etc. That you will hear more about as we get into as I talk about logic and Z3. Yeah. Any questions? Okay. Did we decide on a date for the tutorial, Diganta? I think we should have it on Wednesday.
Yeah.
Now, the tutorial session, by the way, not on, well, I don't know. I mean,
I'll see. I think Harsh has still not come back to me, so I'll ask him to give me a date.
Quickly. And I mean, if we have the assignment, and if there are questions about TensorFlow, both nuts and bolts kinds of issues about the installation, invoking, and so on. I think, maybe Monday or Tuesday we should have one. Okay. And this, by the way, guys, this is optional. And if you have issues, questions, anything about lecture content, material, or specifically about the tools that we discuss, that we introduce, the tutorial is meant for that, very, in an informal kind of setting. And therefore, if you have, you can make use of that. So we will decide on a convenient date and time. So I think you should announce that. It will be at 5 p.m. So that it won't clash with anything else. So, maybe you can have one at least for next week on Tuesday or Monday. I don't know. Monday is too early to align with Hirsch. You can do it on Tuesday, because obviously you can't do it on Wednesday because our class next week is also at 5 p.m. Okay.
Yeah, I'll ask Hirsch, and so yeah, we'll get it organized that way.
Okay. So if you could unshare.
Sir?
Yes.
Yeah, so you were talking about the assignment. Will it be okay if we use PyTorch for the same instead of TensorFlow?
Definitely. In fact, I think so. That's okay, right, sir?
Yeah, I'm okay with it. Yeah,
I think
you should be the judge. Yeah.
Yeah, I think both like PyTorch and TensorFlow, you can use whichever extension, whatever you have more comfortable with.
Yeah. Thank you.
Okay, so if you can unshare, I'll share my screen.
Stop sharing, so I think you can.
Okay. Just to, okay, so a moment. Yeah, by the way, this is, the dates are all screwed up here because we did lots of juggling, where we are pretty much here introducing propositional logic. So next two classes, that is today is 12th and Wednesday is what? Monday is 18th. Oh, well, Wednesday we're already beyond the 19th. No, is it? No, I'm sorry. No. 15th, there is some mistake here. So 15th is a Monday, which is a holiday. 16th, 17th is the next class where we will talk about this one, multi-sorted logic. So I will be assigning some Z3 exercises that you could informally try, after this class itself, so that you will, if indeed you're looking for, if you need that, extra thing about if you haven't taken a logic course and if you're concerned about the thing. I mean, has everyone taken, if there's anyone here who has not had even a discrete math kind of a course that usually people would have had, is there anyone here?
Yes, sir. I haven't had a discrete mathematics or a logic course.
Doesn't have, doesn't know about Boolean logic, for example?
Yeah, I do, yeah.
Who's that?
Rohan.
Okay. So then you should seriously try and pay attention to the next 2 lectures. Okay. Now there will be some symbolisms, etc. Now that you may, I can give you some extra material to read if you are. Don't get scared by the symbolisms. I think you should get the concepts and try to do the Z3 exercises. Yeah. And then take help with the, you can schedule a tutorial. And if you're able to do the Z3 exercises, don't get concerned. Yeah. You should be able to handle the course. Otherwise, if you're taking discrete math courses and then have been introduced to Boolean logic, then you should be able to, with the recap that I do, and after doing these Z3 exercises, you should be able to handle the course.
All right, sir.
Okay. Okay, here's the outline. So I'll start by actually motivating why logic, okay, using an example. Okay, so if you're familiar with Boolean logic like ORs, ANDs, ones and zeros, and so on, so, like used in digital systems and so on, you should be able to deal with. And of course, I will introduce propositional logic in a more pedagogic way that you would see in a logic course. Okay, and then I'll talk about normal forms because they are important to leading to these SAT decision procedures. I have in these presentation, the slide set something about quantified Boolean formula, but I won't be getting to that. Maybe later on we might do that. So you can ignore for now that thing. Everything that I discuss today and in the next class is from that material is from the chapter 1 and 2 of this book. Okay, so if you need some extra material, chapter 2 has a lot more detail. Okay, chapter 1 and maybe half of chapter 2 is what you may, if you refer to the thing. And if you had a logic course, this will be like a recap and maybe give you a slightly different perspective of how we plan to use logic in this course. Okay, so this example that I'm going to introduce you is to make the point that, look, logic is everywhere. Okay, so at least the way I see it. So it touches every day of an aspect of life, and so specifically in that it can be used to artifacts of all kind that we encounter. These artifacts could be situations that you see in everyday life, or it could be programs, DNNs, systems that are implemented and so on. So I use artifact in a general way. So what I want is, here to use logic, how logic can be used to model this kind of a seating arrangement situation. We have 3 chairs and 3 people who we want to seat in these three seats, three chairs, and the seating arrangement, we want to have it in such a way that they meet certain constraints, desired constraints, okay, such as such as these, okay. So first constraint is that there are three people that are numbered 1, 2, and 3, and 3 chairs that are numbered 1, 2, and 3 from left to right, say, okay. And we want one constraint is that person 1 and person 3 should not be seated next to each other. And second constraint, is that every person must be seated in some chair, and no more than one person shall be seated in a chair. So you can think of these kinds of constraints, and then once you have these constraints, then you can ask certain queries about queries involving these constraints. Say that, is it feasible? Is there a feasible seating arrangement such that each constraint or combinations of some of these are met? Okay, for example, here, if there's arrangements such that each of them individually can be met, or combinations of these things met. If there is a seating arrangement, if so, it is feasible, there is at least one seating arrangement, then what are the possible seating arrangements that satisfy these constraints? Okay, are there some seating? Are there some that specific seating arrangements that violate some which be possible seating arrangements? Are there some constraints for which there is no such seating arrangement at all? For example, these are the kinds of things. In this particular example, these were the kinds of queries that we were interested in. Now, if you're looking at a program that you want to prove correctness of test, or DNN, of which you want to prove certain properties of the kind that Diganta introduced about the robustness properties and other thing that he said, then you could still similarly you can express them as queries. Okay, remember that Diganta said SAT queries. Okay, when these kinds of queries are posed to the particular kind of tool that we'll be using to do study verification of DNN, they're called constraint solvers, as there's in the title of the course. Then they're called usually SAT queries, and things that can answer these kinds of things. Okay, so please feel free to stop me at any time, especially those that have not had logic courses. Okay, don't get intimidated. You can stop, and if it is too basic a course and then I want to defer it, I will use that judgment, and we can talk directly, okay, or in the tutorial session to clarify those doubts. But let that not, don't get intimidated in asking those questions, and no question is a stupid question. So if you were to be using logic, now here I'm saying I'm assuming that you're familiar with Boolean logic. I haven't even introduced propositional, Boolean logic is what I call, with a fancy name, propositional logic, okay? And I haven't introduced, but I'm assuming that you know a little bit of Boolean logic. I know that one person said that he doesn't understand Boolean logic, but I think you will get a sense of it when I do it. So first thing is, you want to—
Boolean logic, I think I do understand, like logic gates,
okay.
and yeah, that's fine. Yeah.
Yeah, good. So how do we model such constraints as formulas in this logic? So the Boolean logic has variables that range over, constants 1 and 0, and variables that have Boolean values, and various logical connectives like and, or, and things like that. And any formula that is constructed using those things is what I call as formulas in this particular logic that I'm introducing today. So how do you start modeling, the kind of constraints in this seating arrangement problem that I just now introduced? The first thing is, because in Boolean logic, you deal with variables that take, called Boolean variables, which take 2 values. So So I now I'm using this a set of Boolean variables. I call them xij, and there's one for every person, I ranging over every the person. And together they are 3 times 3, 9 Boolean variables, where xij is true, is the way I use it, is true if and only if person I is sitting in chair J. So if that person I is to be seated in chair J, then this will be true. Otherwise, it'll be false. That's how I'll be using it. Okay. Then, for example, the first constraint, that person 1 and 3 shall not be seated next to each other, can be expressed. It obviously, if a person is sitting in the middle chair, either 1 or 3 is sitting in the middle chair, the other person, will end up certainly being next to that person. Therefore, you can express possibly this constraint using a formula over this variable that you have defined, saying that it cannot be the case that you cannot have, let me see, I have a problem with this thing. Yeah, you cannot have this person, okay, 1 and 3 sitting in the middle position, okay? So, but does anyone see a problem in this thing? I mean, constraint, is it, I'm stating it like this, okay? Here, there is an assumption saying, of course, you could, satisfy and say that even without satisfying an arrangement where, this is true, even without satisfying this constraint, you will be able to seat 1 and person 1 and 3 without making them sit next to each other. Can anyone say how? Oh.
Sorry, so you were saying that even without the constraint, there will be a seating arrangement where 1 and 3 won't
Firstly,
be
are you
sitting next
convinced?
to each other, right?
Yeah, that's right. So yeah. So because there is go ahead.
No. Yeah, so I was saying that, yeah, there will be possible combinations where 1 and 3 won't be sitting next to each other.
No, that is true. But even without, if you're convinced that if this constraint is met, that they, if you want to seat them, they'll certainly not be seated next to each other, correct?
Right. Yeah.
Yeah, but there is one implicit assumption here that everyone is sitting. I mean, you could make them not sit, 1 and 3 not sit by their side, by making them sit one on top of the other, okay? All of them in a single chair, okay?
Okay.
That, we can't, no more than one person can be seated in the other chair. So what I'm saying is, if you're not careful, you see, even without doing it, you can make them 1 and 3 not sit next to each other in the strictest sense where I meant, by making them sit one on top of each other, all in the same chair, okay? So you would have to be careful. That's why the other thing, the other 2 constraints, was made explicit, okay? That, you're right that this one will certainly, guarantee, but it may not be necessary unless you have the other constraint also that you want to make. I mean, these are silly. I mean, but it is important when you're using logic, it'll force you to be very precise, okay? And that is the power and the real value of logic, okay? Because by this picture, it was obvious that's what I wanted, but logic will force you to make these things explicit. That's why you need the other two constraints that every person must be seated in a chair, okay? Because if, I mean, no person, if, I mean, I choose not to seat anybody, obviously 1 and 3 will not be seated next to each other, okay? Do you see what I'm saying? The point I'm making? So that's why, in order to, all the implicit assumptions also will have to be made explicit in order for all these things to make sense. And that's why, we have these other two things, that every person must be seated in a chair, and the third constraint is no more than one person shall be seated, in a chair. So if you want to, so these are the kinds of things, both implicit assumptions as well as explicit things will have to be modeled. But the point I'm making is, you see, already Boolean logic is one of the simplest forms of logics that people in computer science, mathematicians have studied, so that already can do, is able to model quite large class of artifacts, okay, this kind, and even programs and other computational systems. And therefore, so using logic for analysis, by analysis, I mean, analyzing properties of systems, requires you to model, okay, and there's a modeling aspect, and we will very much look at, that's how we'll be using logic, how to model a particular logic. In our case, our object of interest is DNN, okay, and deploying. And then once you model these constraints, the kind of queries, okay, that we were interested in, checking the feasibility of or finding solutions to, we use what are called decision procedures. These are algorithms, techniques, algorithms that once you model constraints, you could, constraints in a particular logic, algorithms to check whether these constraints are true or not. So in this case, see, we were modeling, a particular, these constraints were modeled as formulas such that the solution that we're looking for exactly corresponds to things that, in the situations that make these formulas, the valuations for these variables that make them to be true or false. And that's how we model. And checking those, so that's why we use these, and these decision procedures are algorithms that can automatically check and provide answers to those queries, okay? For example, this question, is there a feasible seating arrangement such that a particular constraint is met, is exactly, in this case, for example, is there some valuation that I can give to these variables xij such that phi1 is satisfied. All three things are satisfied, assuming that we want to see one person, exactly one person in a chair, which is what phi2 and phi3 capture. Given phi2 and phi3, if there is simultaneously, we can meet phi1, phi2, and phi3. And that is what the logical notion of satisfiability is. And decision procedures are able to check satisfiability, okay? And if they're satisfiable, then every possible way that it can be satisfied that can be made true for the various true and false values that you can give to xij to make them true. They are called models, okay? And there are, decision procedures can extract models that make a particular formula true. And in this case, then they can be able to correspond to a different possible seating arrangement to satisfy a bunch of constraints. Okay, so logic talks about model enumeration, finding models, and so on. So a decision procedure can do that. And if there are certain constraints for which there is no seating arrangement to ever possible, that notion is related to something we will hear in logic about, which is called unsatisfiability. A formula is said to be unsatisfiable if there is no valuations for the variables that can make it true. And then the other question, the constraint is met by every possible seating arrangement. That's related to the notion of checking if a formula is valid. Okay, that every possible assignment makes that particular formula modeling a constraint to be true. So you see now, voila, we have all these queries, okay, which can then be reduced to checking these notions that are have been studied in logic for ages, okay? And in the last 10, 20 years, what has happened is mathematicians have actually worked, logicians have worked of various algorithms to check these check these notions on logical formula. And recently, computer scientists have devised on an average, very efficient algorithms that do very nice, just like LP. I mean, LP, linear programming, is very hard, but still there are efficient, on an average, there are LP solvers that can work in practice for a thing. And similarly, these kinds of things can be solved as well. Okay, so so I hope you got an idea of why logic is how logic is useful. Okay, and this is how we will be doing. I mean, we'll be using in for DNN as well. And as we move through the courses, after you see these recap, the first topic that we'll be looking at is how to model DNN in the logic that we'll be using, which is specific logic of SMT, called SMT logic. Any questions before I get in the next 15 minutes or so to start talking, formally introduce this propositional logic in a more formal sense? Any questions? Okay. So usually when you have logic, just like when a programming language, is introduced. So a programming language has a syntax, okay, which tells you how you can construct various expressions and statements, legal, valid, syntactically valid expressions and statements in that programming language. Similarly, logic is very much like a programming language, where there is a bunch of rules that define the valid syntax for various formulas and its components that belong to that logic. And then there is something called semantics, which is relevant in the case of programming languages as well, which tells what is the meaning of this thing. In the case of programming language, what does program, when you execute a program, what does it mean is what constitutes defining the semantics of a programming language. But in the case of logic, since every formula has the notion of when it is expected to be true and when it is false, so the semantics defines the meaning. I mean, the truth assignment way of assigning when a formula is true or false. Okay, and just like in programming languages, you start with the most basic things in the logic, the basic formulas, which are called atomic formulas, and then you build from you have connectives which build bigger formulas from smaller formulas. Okay, from smaller formulas at the bottom, starting with atomic formulas. So in this logic, in propositional logic, you usually introduce for convenience two constants, 1 and 0. Okay, so 1 and 0. It is not necessary that you have to have these constants to define the logic, but it is always convenient to define 1 and 0. Okay, so I've been talking about true and false. Okay, those are logical notions which are kind of different than this syntactic. These are constants in the language that I'm introducing, okay? So these are atomic. And then we have a bunch of variables, which are called as prepositional variables. And we will, so drawn from a finite set of variables, okay? So, formulas meant to be constructed, in a finite tree way using these rules with the variables drawn from a finite set. And these are meant to take two values, true and false. So now if psi is a prepositional formula PF, then this thing where you put this negation symbol around it is also a prepositional formula, okay? And we sometimes use the over line to denote that, okay? So and if psi1 and psi2 are two valid prepositional formulas, then applying a binary operator to those two formulas is also a prepositional formula, where that binary operator can be any one of these logical connectives, or and, which is denoted by this, or implication, and so on. We can get, of course, negation is also can be considered as a logical connective, but it's a unary one, and this is a binary one which taking two arguments. So, for example, so this is a formula, that is constructed. Okay, things like that. So that is the set of formulas. They're recursively constructed, but any particular formula that you construct using these rules after a finite limiting application is a formula of finite size. Okay. Any questions? Okay. Let me move on. Now the semantics. Okay. These can be considered as rules of assigning true and false. So for given any formula phi, see, obviously, these Boolean formulas or prepositional formulas have variables, okay? And of course, the truth and these, semantics it's a function which assigns given a formula true or false. Of course, the formula, Boolean formula, by the way, you use this preposition formula, Boolean formulas interchangeably, so don't get confused. So it depends on the truth or truth assignment to that formula will depend on what the truth assignment to the variables in that formula is. For example, here, whether this formula is true or not very much depends on what value 1 or 0, I mean true or false, that you assign to these variables x, y, and z. And that's why these whatever rules that you give that define the truth assignment to a particular formula, the given formula phi is relative to a particular variable truth assignment to these variables in the variable set. So variable assignment S is actually a function, okay, which assigns to every variable in this set either true or false. Okay, so for example, we use this notation to write this truth assignment is sometimes we also call as the model of the formula, which I will get to later on. Okay, so we write it like this: if Sx is true, Sy is false, and Sz is true. Sometimes we use this notation phi of square bracket S to denote the result of replacing every variable x in F by its assignment given by the variable assignment S. So now we are ready, just like we defined the syntax starting from the atomic formulas and then specifying how larger formulas are constructed. Here we define what the truth assignment is for the atomic formulas, which in this case are 1, 0, and the variable, and then define assignment of truth value to more complex formulas in terms of the sub formulas, into the component formulas. Okay, so that's what this thing does. Okay, and this is the notation that I use. These double square brackets inside which we give a formula, and given an assignment, it defines what it is, if it's true or false. Okay. Yeah. Okay. So I'll go on till 6:15, no more than that. Okay. Since we started late today, I just want to do it. Yeah. I hope you'll bear with me. Yeah, I know I'm cutting into your Friday evening. Please bear with me. So 1 is meant to be true all the time. Okay, that's what the meaning that we want to associate. Okay, I mean, the semantic rules give the assignment. I mean, I can be crazy, and I might want to denote 1 to denote false and 0 to denote true. I mean, why would anyone want to do? But a crazy person may want to do that. But the point I'm making is I will use the standard meaning of 1, which is regardless of what the variable assignment is, since it is not any variable, it is always true. That's what it means. Okay. And similarly, 0 is always has the truth assignment of false. A variable x, of course, the truth, because x is an atomic formula, which has only that variable, and its truth assignment depends on what the variable assignment s assigns, the truth assignment that assigns to that variable x. Okay, so it is whatever sx is. If sx is 1, if sx is true, then that formula x evaluates to true, otherwise it's false. That's what it is meant. So not of psi, given a truth assignment s is true or false, depending upon the subformula of psi for the same variable assignment. If it is false, if that evaluates to false, if that is assigns psi to false, then not of psi has to be true, because that's the meaning that we want to associate with the negation. If the valuation, the truth valuation of psi as assigned by this semantic function bracket is true, then not of psi formula will have it as false. Clear? Okay, if you stay quiet, I'll assume it's clear to you. Okay, and I'll move. So, and a formula which is constructed by building from 2 subformulas using the logical connective and is true if the truth assignments that this function assigns to psi1 as well as psi2, both of them are true. If either of them, the truth assignment of either of those subformulas is false, then this the parent formula will have it is false. So disjunction, the or, is defined similarly. It is true if only one or both of these subform arguments to this or evaluate to their truth assignment evaluates to truth. There's a mistake. There's a small typo here. Pardon me for that. Okay, so any questions here? This is pretty much what I'm doing is recursive. It's an evaluation function that I'm defining that assigns, given a variable assignment that assigns to the various proposition variables in a formula, it evaluates it true. Now you could, for example, you might have the Boolean function, truth tables, okay, are one way of evaluating, or you could plug in 1 and 0, and then you can apply some rules of these things. So for example, this is another way of defining what the truth value of those proposition formulas are, okay? So that's what I've defined, okay? Okay, so now I will define these, these important fundamental notions, logical notions that I already introduced in the context of how they are useful in solving various, finding solutions to these constraints, for solving those constraints in that seating arrangement problem. So we say phi is satisfiable if there exists an assignment S such that phi under that assignment makes it true. That is, if that particular assignment, makes when makes that valuation of phi, the truth valuation, to be true, then it is said to be satisfiable. Okay, that means that is, and it is usually written this way. Okay, and we say that particular variable assignment, in this case, truth assignment of those variables, is called a model of phi. This is all. This is all fancy names. That is as simple as that. Whatever truth assignments to the variables in a formula that, when plugged in, makes it true, is what is fancily called a model. And if there is one such assignment to be satisfied, okay? If phi is said to be unsatisfiable, written this way, if for a particular assignment it is said to be unsatisfiable, that given an assignment S, that formula for that variable assignment is said to be unsatisfiable with the cross across this Chern-Stein symbol if phi of S, as defined by these rules here that I've listed, evaluates phi, assigns the false truth value, truth assignment to this formula. So it's said to be unsatisfiable in general, written this way, which means no matter what, yeah. So if there is no S that can make it, gives it a true valuation, okay? So that is written this way, okay, without any S, which means that for every S, for every possible S, this thing is true, okay? This thing is evaluates to false. So as I said, decision procedures, applied to propositional logic, okay, and that is what Diganta referred to as, a query is a formula, okay, that's all. And a SAT query is a formula drawn from this propositional logic, okay? And a decision procedure, and Z3 is indeed, has as part of it a decision procedure for Boolean logic. For Z3 is a lot, more powerful. It's a whole bunch of compendium of decision procedures, including an LP decision procedures and nonlinear programming. It's a thing, but that's what it does. Okay, it decides. It is a decision. It's various composition. I mean, a combination of decision procedures that at the core just decides these kinds of things. Okay, and that's what we'll be using. And these are very powerful notions. Okay, and so we can model DNNs in these things, and then reduce all our verification problems. In this case, all things that we want to do analyze DNN into some, in terms of one of these notions, satisfiability thing. And I think there is a notion of validity as well. Okay, so if we write that a formula phi is valid, if for every possible variable assignment, in this case for every possible model that you can give for the variables in the formula phi, it is true. Okay, so I have 2 more minutes. Any questions here about these nitty-gritties before I show you some examples? Any questions? Yeah. So one, consequence of the meaning, the semantics that we have assigned for negation, because for the negation we have assigned whenever the subformula, the argument is true, is false, and vice versa. So this notion of unsatisfiability and validity is valid if and only if not phi is unsatisfiable. They are dual notions. Okay? They could be formulas that are both for particular assignments satisfiable, and for some assignments they are unsatisfiable. But we say it is valid, the formula is valid or unsatisfiable only when they are either true for all possible assignments, truth assignments for variables, or they are false for all possible truth assignments. Okay, so here are some examples that I want. Okay, look at this thing, this formula. Can anyone say if this formula is it SAT, unsat, or valid? Anyone dare to want to take a crack? It's too late in the evening. I'll give you the answer. what I'm saying is for SAT, if you're familiar with Boolean logic, it is SAT if there is some value that you can assign to this for x1, x2, and x3 that makes this thing true. Okay, it's getting late, so I'll provide the answer since no one is answering. So for example, this particular thing where x3 is assigned true and x2 and x1 are assigned false will make it true, correct? Believe that? Yes or no?
Yes.
Okay, so it is satisfied because we have found one assignment. Okay, this is, I think, if my guess is correct, it's neither unsat or valid because there are some assignments that also make it false, I believe. Okay, so so that is one. Now this one here is something which is valid. Okay, for all possible assignments, I believe. Okay, because go back into this mode, because if x is, you see, it's if x is false, logical implication, if the antecedent is false, then the way it is defined, implication, although my semantics did not define implication directly, you can express implication, okay, as a connective, and you can define the thing. So normally, if the antecedent, that is the formula, the first formula, I mean, it is false, then it is the logical implication is assumed to be true. Therefore, if x is false, it is vacuously true. Now, if x is true, then you can see by if x is true, then this is obviously true because the second branch is true. Okay, and this whole thing will become true. Okay, because the moment x becomes true, the second argument is true, and because that's a disjunction of two arguments, it becomes true. And that's why for both those things, it doesn't matter what the value assignments for y and z are, and that's why this is a tautology. Okay, validity is something similar. I mean, an equivalent term that is used is tautology. Okay, in Boolean logic, we don't have tautology. Okay.
So I think there should be another. Is there another bracket after, like, right before the outermost odd in this? Because so there should be one closing bracket right before the second odd that is appearing.
I think I might be missing one thing, but does it create an ambiguity? Yeah. I think
it does.
Okay. So I think, see, this whole thing, by the way, is the consequent. Okay. So I guess that's what I mean. Yeah. So first of all, in order to disambiguate, there must be, the whole thing is the consequent of logical implication. And of course, there is a right parenthesis missing. Okay. Yeah, so correct. But the more important one is x is the antecedent, and this whole thing is the consequent. Yeah, that's how I have it. If the closing bracket parentheses is here at this point, okay, so if this closes here, even then this might be valid. I don't know.
Yeah, even then this is true.
I think even then it is probably valid. I mean, it is a tautology. And you can see that phi 3, this formula, is unsatisfiable because the way that this various things are there, there's a circularity in here. So if B is true, of course, this is a conjunction of this is a conjunction of 3. I'm sorry, 1, 3. See, if C has to be false, right, in order for this thing to be true, because it's a conjunction of but if C is false, this disjunction is, I mean, so for it to be true, A has to be false. If A is false, then you will see B has to be false in order to make this one true. If if B has to be false and C has to be false, this can never be true. And therefore, so this one, phi 3 is never true for any assignment. And that's why you can do this. So there are some exercises for which that I have given here. So I'm going to stop here. So please, if you're, if you want to kind of get acquainted, I say get acquainted because I'm not going to, this course will not involve deep questions, will not explore deep questions about logic, completeness, compactness, expressibility. In a formal logic course, there will be proving theorems about logic and so on. We will not be doing that, okay? But this course will be applying those concepts, but you have to get acquainted with these things. And the only way that you can get acquainted is by trying out examples on this tool, as well as try every example that I give. I have a whole bunch of examples, exercises that I can give you, okay? And if you want very much interest in the course, but you feel that you don't have enough logical background, that is what I will tell you. You should never don't be lazy to work out examples, okay? Both to model situations as well as try out these things. So as a first thing, you can start by not looking at the slide and then trying to do these three things, okay? I've given the solution, but you can try it out with Z3 and so on, okay? This is where I'll stop, okay? I know that I went beyond my time by 5 minutes, so you can reserve the questions until for later, okay? So I'll stop sharing. Stop recording.